Yeah, good afternoon, everyone. Thank you very much for coming to this new colloquium of the Mathematics Department of the University of Buenos Aires. And today we have the great pleasure to receive Professor Dmitry Jakobson from McGill University. And he will give us a lecture about eigenvalues in conformal Laplacian. Thank you very much, Dmitry, for coming.
Thank you.
Switch on your...
I think it's on. Thank you very much. I'm Dmitry Jakobson from Montreal. It's my first time in Buenos Aires, so thank you very much for the invitation. I will speak about some results that are joined with several people. Some of my main collaborators was my former student Shaisa Kanzani, who came from Montevideo, and Rod Gover from New Zealand, from University of Auckland. So we wrote a first paper a couple years ago, and then we were slowly developing all this stuff. So most of the time I work on eigenvalues, eigenfunctions of Laplacian. But now I will speak about kind of slightly more geometric version of Laplacian, which comes up in conformal geometry called conformal Laplacian. And then I will speak about nodal sets of eigenfunctions, so the set of points where an eigenfunction of conformal Laplacian is equal to 0, and how it appears in how it is useful in conformal geometry. So I have to explain what is nodal sets, I have to explain what is conformal geometry, and I have to explain how they are related. So to explain about nodal sets, let me show you a movie. This movie is somewhat interesting because the first version of this movie was shown by Ernest Chladni about 200 years ago. So at that time, so let me pause and explain what is going on. So these are the so-called vibrating plates. So you put a metal plate, and you start, now you can just turn on a sound generator which will emit the sound at a certain frequency, and the plate will vibrate. And then an eigenfunction of Laplacian is an amplitude of vibration. So if you play the drum, then this drum, the surface of a drum, sort of goes up and down, and the height by which it goes up and down is an eigenfunction of two-dimensional Laplacian, or actually a square of Laplacian, to be perfectly honest, but let's pretend that it's Laplacian. So now what Chladni was doing, well, he couldn't, 200 years ago there was no sound generator, so he was playing it, he was using the bow of a violin to excite the vibrations on the plate, and he had to be very good, he had to play his bow exactly at a given frequency, so that you would see some pattern. Now, if your frequency of oscillation coincides with the frequency of vibration, then you can see some interesting pictures. Now, where these pictures come from? You put some powder on top of the plate, and so suppose I'm a small piece of salt, or whatever, lying on top of the plate, and the plate is vibrating. And so if the amplitude of vibration is non-zero, then I'm jumping up and down, so then my position at the plate is not very stable. So I would like to move to a point where the amplitude of vibration is 0, and that is the point where an eigenfunction of Laplacian, which gives you the amplitude of vibration, is equal to 0. So the particles tend to fall off to the curves where an eigenfunction of Laplacian is equal to 0. And these are the curves that you see. Now, if you change the frequency, then an eigenfunction changes, and the curve where it is equal to 0 changes as well. So if you go to the next frequency of vibrating plate, you will see a very different picture. And so let me if you don't hit the right frequency, then the picture becomes blurry. So you have to hit the next exact frequency of the plate. Let's see, and the sound becomes very annoying. Oh, can I? Anyway. Anyway, so you get the idea, right? Let's see. So let me quit this one. Let me quit this guy. And the same thing happens if you have water, let's say coffee in a cup, and you look at the surface of the fluid of the water, and then you can also emit a sound, and you can look at the waves that form on the surface of the water, and then if you scatter light, then the dark parts of the picture would be the lines or curves where the water, the surface of the water is kind of stationary, where the amplitude is 0. So that's experiment number 2. So it's a round cup. The green thing is the sound generated, and if you separate variables in a round billiard, in a disk, your eigenfunction will be a product of Bessel function and sine and cosine, and so the circles you see are zeros of Bessel function, and the lines you see are equal angles where sine or cosine is equal to 0. So anyway, and you see as the frequency increases, these nodal lines become kind of more and more dense and more complicated and so on. Chladni published the first book on acoustics, where he wrote down lots of such pictures. He never worked at any university, never had a university position. So the way to make his living was to go from one city to another and give this performance. And since there was no YouTube 200 years ago, the only way to see this was to go and see in person the concert by Chladni. So no pirate videos existed at the time, which was fortunate for him, I suppose. He received a big grant from Napoleon for translating his book on acoustics into French. And then there was another grant from the French Math Society to explain what are these strange lines that you see in this picture. And so I think this grant, Sophie Germain received this grant for explaining the nodal lines of Laplace eigenfunctions in an ellipse or something like that. So she did a special case. If the plate is very irregular, then there is no closed form expression for these nodal lines, but they're still interesting. You can prove stuff about them. Anyway, so these are nodal lines of eigenfunctions of Laplacian. So, and some people still use them to tune violins, and this is, seeing the sound. So I've been to Venice to Biennale, and there was an installation in the Biennale which had these Chladni plates. There was a drum. Someone was singing, and that was exciting the surface of a drum, and there were some seeds, so it was very artistic, but kind of the same picture. So the Chladni plates made it to Biennale in Venice. So okay, some success. Anyway, so these are nodal sets, right? So that was part 1. Part 2 was conformal geometry. Should I explain what is a Riemannian manifold? It's like a curved surface, right? So at every point you have an inner product. Inner product in a local coordinate system is a symmetric positive definite matrix, which for any two vectors, u and v, would give you an inner product between u and v. Now, a conformal change of metric is a change of metric that preserves angles but may change length. Now, if you have two vectors u and v, then cosine of an angle between two vectors u and v is equal to the inner product between them divided by the product of their norms, correct? Now, let us take a point. Let's multiply all inner products by the same positive number. Let me call this positive number t squared. Then the inner product between u and v will be multiplied by t squared, and both norms, a norm is a square root of the inner product of vector with itself, right? So both norms of u and the norm of v will be multiplied by t. So when we divide, t squared will cancel t times t in the denominator, and so the angle gets preserved. Is this all right? So one way to, and conversely, if you want to preserve angle between any two vectors at the same point, then the only thing you can do is you multiply all the inner products at that point by a positive number. But the positive number can depend on a point, right? So at this point, I can multiply all the inner products by 10, and at that point, I can divide them all by 2019. Correct? And so a conformal class of metric is a given Riemannian metric, so at every point you have an inner product, multiplied by a positive function. So your sort of degree of freedom is multiplication by an arbitrary positive function on a manifold. And if two metrics differ by multiplication of the positive function, they're called conformally equivalent. So the lengths of curves change, but the angles between curves stay the same. So if the two curves were orthogonal, then they stay orthogonal in the for a conformally equivalent metric. Okay? Very good. Now, in dimension 2, there is a nice formula that if you take a metric G1 and it is conformally equivalent to the metric G0, so they differ by multiplication by a positive function. Let me call this positive function an exponential of something. Okay, so let me write a positive function as e to the 2w times. So the two metrics differ by multiplication by a positive function. Then the Laplacian, the two-dimensional Laplacian, so here the dimension of the manifold is 2. The Laplacian for the metric G1 is e to the minus 2 omega times Laplacian for the metric G0. So if you multiply the metric by a positive function in 2 dimensions and 2 dimensions only, Laplacian is divided by this positive function. For example, take the metric in take the negatively curved plane, upper half plane. So it's a model of hyperbolic plane where curvature is -1. The metric there is Euclidean metric divided by y squared. So the Laplacian for the hyperbolic metric will be y squared times the Euclidean Laplacian. Okay? I'm sure you may have seen pictures of hyperbolic metric upper half plane model, or there is a model in a disk which Escher liked, and things like that. But if you take Laplacian on a manifold of dimension 3 or higher, then and you change the metric conformally, then the if you want to write Laplacian for this new metric, conformally equivalent, then you will have a gradient term. So the transformation law will look a bit more, will be a bit longer. Now, I'm a mathematician and I'm a very lazy guy. So I'm asking, okay, can I change the Laplacian by adding some potential? so that after I change my operator, the transformation law will become a little bit more similar to the transformation law in dimension 2. And the answer is yes. And the way to do it is to write a conformal Laplacian instead of Laplacian. So to the Laplacian, you add a potential which is a multiple. So it's a Laplacian plus let's see, anyway. Doesn't matter. It doesn't matter so much. So it's a Laplacian plus a constant. This constant is 0 in dimension 2, right? Because for this fraction, the denominator is let's see. So this Rg is a scalar curvature of a metric G. And the constant multiplying the curvature vanishes in dimension 2 because there is a multiple n minus 2. So in dimension 2, we just have the usual Laplacian, nothing changes. But in higher dimensions, if we add, so this is like a Schrodinger operator, right? So if we take a Laplacian and add to it a multiple of scalar curvature, then the transformation law, and if we change the metric conformally, then the transformation law for the Laplacian becomes like that. So suppose you take some test function u, and you would like to act by the Laplacian for the new metric on this test function. Then what you should do is you should take the test function, multiply it by a positive multiple of the conformal factor, and then on this product you should act by the conformal Laplacian for the old metric. So you apply old Laplacian to this product. And then the result is a function. And that function you multiply again by something positive, now by a conformal multiple raised to a slightly different power. So it's e to the minus n over 2 plus 1 omega times that. So this is the transformation law for conformal Laplacian in dimension bigger than 2. So it's in dimension 2, we didn't have to multiply, we didn't have a positive multiple inside. But now, by adding this transformation, we have removed the gradient term in the that we had for the transformation for conformal changes of metric for the usual Laplacian. Conformal Laplacian sometimes is called Yamabe operator, so it's very useful in conformal geometry. It comes up a lot. And then, so any operator which has a transformation law that, P G1 is like e to the a omega times an operator for the old metric times e to the b omega for some constants, a and b, which depend on dimension. Such operators are called conformally covariant. So the simplest one is conformal Laplacian. So my talk today will be about conformal Laplacian, but you can have a sort of a conformally covariant version of Laplacian squared. This is called Panit's operator. And there are some operators which start, with Laplacian raised to the power 3, and sometimes even half-integer powers of Laplacian and fractional powers of Laplacian. So there are higher order operators like order 4 or order 6, which have similar transformation formulas. But today will stick to conformal Laplacian because that's the simplest and the most basic one of them. All right. Now, so if we take the usual Laplacian, no potential, we know that all the eigenvalues of Laplacian are non-negative. And the only way an eigenfunction of Laplacian can have eigenvalue 0 is if this function is constant, right? This is true. But so now we have taken a Laplacian and added some potential. So potential can, it's a multiple of scalar curvature. In hyperbolic space, scalar curvature can be negative, right? So there is a, in dimension 2, there is a uniformization theorem that in every conformal class on a surface, there is a metric whose curvature is constant. In higher dimensions, there is a similar result which says that in every conformal class there is a metric called Yamabe metric where the scalar curvature is constant. Now, suppose the scalar curvature is constant and negative. Then what are you doing? You are taking Laplacian and subtracting just a negative multiple of identity operators. So what is happening is you keep exactly the same eigenfunctions, but a positive eigenvalue that you had is moved a little bit and can become negative, became smaller, and some of them can actually be negative. And it can happen that one of the positive eigenvalues after you moved became equal to 0 if things aligned exactly, right? So if it's equal, if it happened to be equal to exactly the constant we're subtracting, then eigenvalue, so it is possible for an eigenvalue of conformal Laplacian to be 0. And the functions need not be constant, unlike the usual Laplacian. Okay, so now here is a very, very simple remark. Suppose I had an eigenfunction of an old Laplacian, of conformal Laplacian for the metric G naught that with eigenvalue 0. So if I took this function and applied conformal Laplacian for the metric G naught, then I get an identically 0 function. Now, suppose I change the metric conformally, then then there is the following very, very simple remark that if I multiply my old eigenfunction of Laplacian with eigenvalue 0 by the reciprocal of the conformal multiple that appears inside, and I substitute this product into the transformation formula, then the power of conformal multiple that is multiplying the function, I divided it because it's a positive function, so I can divide by it. So the two positive functions cancel each other. You get 1. So you get the conformal Laplacian for the old metric, and you're applying it to a function that lies in the kernel. You get a 0 function. So the result is an identically 0 function. And then you take a 0 function, you multiply it by something positive. Well, you still get a 0 function. So we use, very sophisticated results in our work that 0 times something is still 0. It's extremely important thing. You should really remember it. Okay. And so the corollary is that if the original conformal Laplacian had a non-trivial kernel is always a finite dimensional eigenspace, because even though you added a potential, it's still an elliptic operator. So every eigenspace is still finite dimensional. Then the kernel for the transformed metric, you should take functions in the old kernel, multiply all of them by something positive, and then these products will become the kernel of the Laplacian for the new metric. Now a question to the audience. Suppose you take a function which lies in the kernel, and if you look at all metrics in the conformal class, you can multiply your function by any positive function whatsoever on your manifold. What remains invariant? Hint, you saw the answer in the movie. It's the set of points where the function is 0, right? Because if you look at the level curve, for example, where the function is equal to 1, and I can multiply by something positive, then after multiplication by a positive function, it's not 1 anymore, so it's going to change. But if the function is 0, if I multiply by anything positive, it's still 0. Right? So remember, we were using that 0 times something is 0. It's a very useful thing. So the nodal set of an eigenfunction remains invariant, is a conformal invariant. Now, for some reason, the fact that the kernel changes like that was known to, like, Nigel Hitchen wrote this paper about Dirac operator in 1970 when I was born. I was not interested in Dirac operator when I was half a year old. I was interested in some other things. So for some strange reason, no one noticed for quite a while that when the functions get multiplied by something positive, their nodal sets remain invariant. Maybe they noticed but didn't write. Anyway, so so we wrote it down. Not only the nodal set, you see another thing which remains invariant is a sign of an eigenfunction. So if an eigenfunction were positive at some point, if we multiply by something positive, it after multiplication by a positive function, the sign is preserved as well. So if you look at eigenfunction of Laplacian, then if you remove the nodal set from a manifold, then the manifold breaks up into connected components, and those are called nodal domains. Right? So imagine that everyone an eigenfunction, a manifold is a pie, is a cake, and so we cut the cake along nodal sets of some eigenfunction. Then what remains after we cut the cake are pieces of the cake. And so every piece of the cake, on every piece, eigenfunction on this piece, eigenfunction is positive, on the next one it's negative, then it's positive, and so on. Right? So if the nodal sets are lines on the floor, then the tiles, the square tiles on the floor, would be nodal domains. If you take eigenfunctions in a rectangle, which is a product of sines and cosines, that's how the nodal set will look like. It will be like a grid of streets in the city, or, you know, tiles on this floor, and the nodal domains will look like these little squares or rectangles. But in general, nodal lines can be very curved, like you saw in the movie, and so nodal domains will be more complicated. But whatever they are invariant. If the eigenvalue is 0. If the eigenvalue is not 0, the whole thing goes out the window. Okay? We can say nothing, because there is no good transformation rule. Right. You can say a little bit more. Suppose you have two eigenfunctions with eigenvalue 0, which are linearly independent, which are not multiples of each other. Right? Then what you can do is you can take two functions at the point u1 of x and divide by u2 of x. So you can look at the ratio of the two eigenfunctions at a point. Now you change the metric. Now both eigenfunctions get suppose I have changed my metric, then all eigenfunctions got multiplied by some positive number, but that positive number is the same for both functions, right? Because all the eigenfunctions in the kernel at a point get multiplied by the same positive thing. So e to the n minus n over 2 minus 1 omega times an eigenfunction for the old metric. And so the positive multiples cancel, and the ratio remains the same. Now, so to turn it into a theorem, what should we do? We should say, okay, let us take a manifold and remove from the manifold the intersection. So suppose we have a kernel of conformal Laplacian. It's a finite dimensional space. So suppose the dimension of the space is some number, let's call it k. And suppose the kernel of Laplacian is spanned by functions u1, u2, uk. Then I should remove the intersection of all the nodal sets of the eigenfunctions ui, when I remove the intersection of all the nodal sets, then on the remaining part of the manifold, at least one of the eigenfunctions is different from 0. Correct? Because if all of them are 0, then that point lies in the intersection of the nodal set, and that I have removed. That set that I have removed is conformally invariant. Now, on the rest of the manifold, what I could do, I could use eigenfunctions of Laplacian as projective coordinates. Right? Because so eigenfunctions themselves are not invariant, but their ratios are invariant. And so what I could do, I could say that the point x, phi, I can define a map. Phi of x is u1 of x, u2 of x, and so on, uk of x, and that gives a conformally invariant map from a manifold into projective space whose dimension is 1 less than the dimension of the kernel of the conformal Laplacian. Is this okay? So strictly speaking, this is defined up to choosing a basis. So there is a general linear group acting on the space of functions uk, which basically says, okay, I can change the basis from u1, u2, uk to some linear combinations of these functions. And so what is invariant is the image of the manifold under the action of GLK in the projective space, PGLK. So that thing is conformally invariant. And another thing is that if I change the metric conformally, then the volume form is multiplied by some positive function. And so what I can do is and eigenfunctions in the kernel are also multiplied by something positive. So if I raise an eigenfunction in the kernel to a suitable power, like take the suitable LP norm, that LP norm will also be conformally invariant. And actually restricted to any subset of manifolds. So integral of the Pf norm of eigenfunction over any subset, not just the whole manifold, but any subset, that will be conformally invariant as well. So if the eigenvalue is 0, we have a certain supply of conformal invariance. Now, so that was part of the PhD thesis of my student. And you know, what's every student's worst nightmare? You prove a couple of theorems, but there are no examples. Right? So you ask, okay, so how often can we have eigenvalue of conformal Laplacian equal to 0? That question is related to the negative eigenvalues of conformal Laplacian. So you see that if scalar curvature is negative, then it can sort of try very hard and bring some of the positive eigenvalues and make them negative. But eventually Laplacian is going to win over the potential. And so eventually eigenvalues become positive, and eigenvalue asymptotics like Weyl's law, they are similar for the conformal Laplacian and the usual Laplacian. Now, but there may be finitely many negative eigenvalues of conformal Laplacian. Their number is also conformally invariant. That's another thing on this slide. After we did all that stuff, we found out that actually it was not known where for generic conformal class 0, so you believe that 0 is not an eigenvalue of conformal Laplacian for a generic conformal class. But this is something we had to prove in a subsequent paper, so we did it. For other operators, this is for Dirac there are related results. For Panit's operator for the square, kind of conformally invariant square of Laplacian, that is not known. The constants are always in the kernel, but the question is, can you have something else? Maybe for generic conformal class there are just constants in the kernel and nothing more. And I think this is a question of people being lazy. My student has finished and moved on to other things. So maybe I need to give this problem to another grad student. Anyway, so now the question about how often 0 is an eigenvalue of conformal Laplacian is related to the question of how many negative eigenvalues can a conformal Laplacian have. And here is an interesting result. So the number on any compact manifold of dimension 3 or higher, the number of negative eigenvalues of conformal Laplacian cannot be bounded above. So it can be bigger. So you give me your favorite positive number, 10 billion and 6. And then I find a metric, and you give me your favorite manifold of dimension 3 or higher. I don't know, 3-dimensional sphere. Then on a sphere, there exists some strange metric where the conformal Laplacian for that metric will have at least 10 billion and 6 negative eigenvalues. Maybe more, maybe it will have 10 billion and 7. That I do not know, but at least 10 billion and 6. There are two proofs. That's not our result, that there are sort of two results in the literature. One result, so there was a wonderful theorem due to Yves Caland-de-Vertière, which said the following thing: take a sequence of positive numbers, non-decreasing. Then on any compact manifold, there is a Romanian metric such that the first k eigenvalues of Laplacian are exactly those k numbers. So give me a sequence of 100,000 numbers, then on any manifold of dimension 3 or higher, there is a Romanian metric where those 300,000 numbers are the first 100,000 eigenvalues of Laplacian. So by looking at the initial set of eigenvalues of Laplacian, you cannot say very much, because any set of these numbers can be realized as the first k eigenvalues of Laplacian. So one result of Locamp says, in addition to making your eigenvalues those numbers, you can make Ricci curvature very negative definite. Okay, and scalar curvature is trace of Ricci. So if Ricci is very negative definite, Ricci is a quadratic form. So all the to take a trace, you add all the eigenvalues of Ricci curvature tensor. And then if all these eigenvalues are very negative, if you add them, you get something which is also very negative. And if you make all your eigenvalues small and subtract 1 million, well, you'll have a lot of negative eigenvalues of conformal Laplacian. But that is kind of it's a little bit of an overkill. So the result is perhaps too sophisticated. So there is a slightly more intuitive way of doing things, of making negative eigenvalues of conformal Laplacian. And the way it's done, I like to call it, my name for it is growing mushrooms. So what you do is you take your favorite manifold and you attach a sphere. So it does not change the topology, but on that sphere you make the scalar curvature very negative. And then maybe you attach another sphere at a different point. And on that sphere you can also make scalar curvature very negative. So if you attach several of such spheres, that gives you a space of test functions on which the conformal Laplacian will be negative definite. And so that by sort of min-max theory, that would say that there are several negative eigenvalues of conformal Laplacian. And the more mushrooms you grow, so the heavier the rain, the more mushrooms you see. And so each mushroom results in at least one maybe negative eigenvalue. So to get more negative eigenvalues, you should attach lots of these spheres, so you should grow a lot of mushrooms. So that's one way of doing things. So that was in the paper by El Sayed, second eigenvalue of Humabe operator and applications. So now, sort of a little remark is that in dimension 2, if you mod out by changes of coordinates, if you mod out by diffeomorphisms, the space of conformal classes is finite dimensional. This is the Teichmuller space, right? If the dimension of the manifold is 3, and if you look at conformally equivalent metrics and mod out by diffeomorphisms, the resulting space is still infinite dimensional. So Yeah, what I claim is that this infinite dimensional space is a little bit like, pavilion number 1 at UBA. Why does it look like it? Well, so we're in this room. So for all the metrics in this room, conformal Laplacian has exactly, 5 negative eigenvalues. And in the corridor, conformal metrics for metrics in the corridor, conformal Laplacian has 6 negative eigenvalues. Now, to go from the room into the corridor, you need to open a door. I think this is maybe a fire escape, so I don't want to open it, but maybe I can open another door. And when you do it, one of the positive eigenvalues crosses 0 and becomes negative. Okay? So that means that, and since the number of negative eigenvalues can be as high as you want, that sort of has to happen infinitely often. Right? So you can have a curve in the space of metrics, in the space of conformal classes. Conformal class has to change, because in a conformal class, the number of negative eigenvalues is fixed. So you have to start with a metric with 3 negative eigenvalues, and then you connect it by a curve to a metric which has at least 4, and then at least 5, and so on. So and so every time somewhere along the curve you had to cross this wall, and somewhere you had to have eigenvalue 0. So even though all our results are about metrics where conformal Laplacian has eigenvalue 0, somehow there are infinitely many. So the whole space of conformal classes is divided into by hypersurfaces where conformal Laplacian has eigenvalue 0, and in the complement, the number of negative eigenvalues is fixed. But there are infinitely many such hypersurfaces, so at least we have lots of examples for all the results that I mentioned in the beginning. And so that means that at least the set of examples to all our theorems is non-empty. But it's reasonably big. So that's always good to know, right? For other operators like Panitz and so on, we do not have such a general result. We only have it in some special examples, on some special kinds of manifolds where we can sort of do things by hand. Okay. Now, so another remark is so there is a topology on the space of metrics which is called Gromov-Hausdorff topology. And in this topology, it's one of the ways of using this topology is that if you make some assumptions on certain sets of metrics, then those sets of metrics become pre-compact. So if you have a bounded sequence of metrics, then it has a conversion subsequence, like real numbers. And that's convenient. So compactness results are always convenient if you work in calculus of variations or something, or if you look at how manifolds degenerate and so on. So here is a very, very simple remark. Suppose you have a sequence of metrics where the number of negative eigenvalues of conformal Laplacian is increasing, right? And suppose you normalize sectional curvature, scalar curvature to be -1. Because in every conformal class, the number of negative eigenvalues is fixed, so you can choose any metric in a conformal class that you like. So, for example, we can choose this Yamabe metric where the scalar curvature is -1. If the sequence of negative eigenvalues of conformal Laplacian is increasing, then that sequence of metrics cannot be pre-compact in Gromov-Hausdorff topology. So one way of thinking about it is like this, suppose you get into your car and you start driving, I don't know, to Patagonia, right, on a highway. And you drive, and it's a long road, and on the road, there are signs you're saying you're like 3 kilometers away or 5 kilometers away or, 100 kilometers away from Buenos Aires. let's, you know, I'm from Canada, so I will start in Montreal and drive to Vancouver. It's also a long drive. But you know, there will be some sort of highway sign saying how many kilometers or how many miles or whatever I have passed. So if you drive in this infinite dimensional space of conformal classes, maybe there is a little sign on the road saying that, okay, so this is 5 negative eigenvalues of conformal Laplacian, 6, 7. So if the number is increasing, that means that you are not coming back. So you're sort of moving forward in some direction. That's, of course, the things are not so simple. Luckily for us, the surface of planet Earth is two-dimensional, not infinite dimensional, because otherwise it's going to be a little bit difficult to navigate. But still, I think the number of negative eigenvalues of conformal Laplacian could be a nice, you know, an interesting thing to look at, not just saying that scalar curvature is negative, but this is sort of giving it a way of quantifying how negative your scalar curvature is. So this is sort of fairly modest thing. Now, so here is a question which, in my opinion, is interesting. So in general, it is known that making scalar curvature positive is not so easy. So there are lots of manifolds that do not have Romanian metrics of positive scalar curvature. Like most three-dimensional manifolds do not have any metrics of positive scalar curvature, but some of them do. And in some dimensions, it was shown by Gromov and Lawson that sets of metrics with positive scalar curvature can have infinitely many connected components. So on the other hand, it is known that the set of metrics with negative scalar curvature is always contractible. So you can think of maybe, I don't know, the set of metrics with negative scalar curvature as some sort of ocean, and positive curvature are maybe, I don't know, ships or islands or something, or I'm not sure. So the set of metrics with negative scalar curvature means conformal Laplacian has at least one negative eigenvalue, right? But suppose you look at the set of metrics where the conformal Laplacian has no more than 3 negative eigenvalues. Is that set of metrics connected or not? So I think this is a little refinement of this question about so this is like these guys do not have positive curvature. Positive curvature means 0 negative eigenvalues. So all eigenvalues of conformal Laplacian are positive. But now you can say, well, okay, suppose I restrict the number of negative eigenvalues, it's at most something. Is that set connected? So I think it's also a reasonably interesting refinement of that question. Okay. Application to curvature prescription. So curvature prescription, sometimes this is also known as Nuremberg problem. So Louis Nuremberg was an undergrad at the same university where I work, McGill. In the year 1941, he moved as a grad student to New York and stayed. And then a couple years, so he won the Abel Prize. He's a very good geometric analyst. A couple years back, we wrote to him saying we would like to have lectures on geometric analysis. We would like to name them after you. Do you mind? He said, yeah, okay, fine. Came to the first few lectures, and so at one of the lectures, the speaker said that Louis Nuremberg liked tango very much. And I said, okay. And so at the next lecture, I invited some of my teachers, and they gave a little demo at the reception after. But Louis is in a wheelchair, and he used to be a very good ballroom dancer when he could still dance, but he likes kind of watching tango. But last lectures he could not come. He was in the hospital, unfortunately. He is kind of a fairly old guy. Anyway, so Nuremberg problem is find a metric on a surface where the Gauss curvature is a given function. So this is prescribing Gauss curvature. Now, a higher dimensional version of that is find a metric where the scalar curvature is a given function. So this is prescribing scalar curvature, right? So scalar curvature is like a higher dimensional analog of Gauss curvature. We can make, but scalar Gauss curvature in dimension 2 is kind of, it tells you a lot. Scalar curvature in higher dimensions, since you have it's a trace of a matrix, so this is kind of a much weaker invariant. So scalar curvature, you have too many degrees of freedom. So saying something about scalar curvature doesn't give you as much information. So you can make this problem in higher dimensions a little bit more difficult by saying, okay, let's find a metric with a given scalar curvature in a given conformal class. Okay? So this is like a problem on the test, but you just, the professor made it more difficult, so life is hard. Okay, now, so here is a result. Suppose in that conformal class where we want to prescribe a scalar curvature, conformal Laplacian happens to have an eigenvalue 0. And, we have a couple of examples by the previous stuff. Then take an eigenfunction that lies in the kernel and take a nodal domain, right? So remove the nodal set. The manifold will break up into pieces. On each piece, an eigenfunction is positive or negative. And suppose you would like to prescribe scalar curvature. Then in any nodal domain, the function that you would like to prescribe as a scalar curvature somewhere would have to take a negative value. So this function could not be positive everywhere in the nodal domain. Otherwise, you would get a contradiction with some result, kind of green type formula. There is a similar result where you do not make this requirement that you would like prescribe it in a conformal class. This is called Trichotomy Theorem. So how much time do I have? 5-10 minutes. Well, let me skip this. There is a general theorem about prescribing scalar curvature without restriction to conformal class, and this more restricted version in a conformal class is kind of reminiscent of this more general trichotomy theorem due to Kasdan and Warner, but maybe let me skip that. Let's see. Now, so recently I had another student, and we could do we could prove lots of related results for manifolds with boundary. And since I have 5 or 10 minutes remaining, actually let me skip over that part. So we had a couple of examples of conformally covariant boundary value problems, and then we could prove some analogs of various results we had for manifolds without boundary, and then we also had some results about comparing the number of negative eigenvalues for 2 different boundary value problems, and that was equal to the dimension of the kernel of some sort of conformally covariant Dirichlet to Neumann operator. So these are so this is sort of conformally invariant version of some results due to Friedlander for the usual for the difference of eigenvalue counting functions for Dirichlet and Neumann problems for the usual Laplacian for manifolds with boundary. So we have a conformally invariant version of that. So we developed a little bit the whole thing for manifolds with boundary, but so let me actually skip all that because this is more technical, and this we should have some coffee or something. But let me finish with a graph theory version of this whole business. Now, so what's a graph? A graph is a set of vertices connected by edges, right? And when people do, when you draw pictures on your computer, what happens is you discretize your surface, right? And then you connect, so you have a bunch of points on your surface, you connect them by lines, so you get some sort of triangulation of your surface. So now, when you do triangulations, then you sort of do a discrete approximation to your Romanian metric, and then some people may be interested in drawing surface in such a way that the angles between curves are preserved. So some people may be interested in discrete version of conformal geometry. So to be able to say that the angles are preserved. So to do that, you have to define what's a conformal transformation. Now, so if you have an edge connecting two vertices u and v, then every edge has a weight which usually is a positive number. So think of a graph as some sort of as some sort of electric resistance, some electric chain, electric circuit, and then the length of an edge or a weight of an edge is electric resistance. One way of thinking. But combinatorial graph, the weight of every edge will be equal to 1. But if you draw something or if you do electric circuits, it doesn't have to always be equal to 1. It can be some positive number. Now, so we say that and the metric on a graph is just for every edge you get a positive number, and that's a weight of that edge. So that's one way of thinking of. Now, two sets of weights on the edges of the graph are conformally equivalent if the following thing happens. So there is a function from the set of vertices of the graph into reals, and that function is basically a logarithm of conformal multiple. So if the new weight of an edge should be exponential of function at one endpoint plus function at another endpoint times an old weight of that edge. And the way to think is that if you triangulate your surface and your graph is kind of dual to that triangulation, then here you make everything longer by e to the f of u, and here in that triangle you make everything longer by e to the f of v, and so the edge sort of gets some sort of average. So this is sort of intuitive way of thinking, but this is actually what people use in image processing and so on. So the question is, can you have some operators on a graph that will satisfy a transformation rule similar to the transformation rule for the conformal Laplacian in the continuous case? Right? So do we have any interesting examples of operators on graphs which, once we have the transformation law, a similar transformation rule, then we can sort of turn the crank and outcome the theorems, which kind of discrete versions of the same theorems. So what you need are some examples. And so we have discovered a few such examples. So one very simple is adjacency matrix. It defines a random walk on a graph. Another is, so Laplacian on vertices, vertex Laplacian on a graph doesn't have this transformation property, but the Laplacian on edges does. And also there is another thing called incidence matrix and so on. And okay, so you can ask, okay, what's a nodal set of an eigenvector? So an eigenfunction, the continuous eigenfunction, becomes an eigenvector on a graph. So we say that a nodal set lies on a certain edge if an eigenvector at one end is positive and at the other end is negative. So somewhere across the edge it has to change sign, so the nodal set has to be located somewhere on that edge. and so that nodal set becomes invariant, and so on. So you have so we have a paper in geometria dedicata with a couple of summer students, with some of my summer students a couple of years ago, where we wrote down some discrete versions of these results. Thank you very much.
Is there any question or comments?
I'll ask this question. Sorry, what is the edge Laplacian?
The edge Laplacian. So there is a there is a matrix which is kind of a discrete analog of a differential. That matrix is rectangular, and its size is number of vertices by the number of edges. Now, if you start with rectangular matrix, you can make it into a square matrix in two different ways. You can multiply A by A transpose, or you can multiply A transpose by A. In one case, you will get square matrix whose size is number of vertices. If you do it the other way, you will have a matrix whose size is number of edges by number of edges. And number of vertices by number of vertices would give you the vertex Laplacian. And number of edges by number of edges would give you the edge Laplacian. So it's like d star and d star d. So it's a discrete version of that. And then it turns out that this rectangular matrix is multiplied by something diagonal on one side. And if you do A times A transpose, then this diagonal becomes inside, and you don't have a good transformation law. But if you do it the other way, then for this matrix product, you multiply on both sides by two diagonal matrices, and that means that this is like multiplying by two positive functions in the transformation formula in the continuous case. So that gives you a discrete analog of this thing. If you want details, I can send you all the papers are on my homepage, and I think a bunch of them are in archive and blah blah blah. So I can send it everything. It's all very simple. The thing is that I go to New Zealand from Buenos Aires, and my co-author Rod Gover is an expert on conformally covariant operators acting on differential forms. This is called tractor calculus. This subject is extremely technical. The calculations are quite difficult. And I'm a lazy bum. So for as long as possible, I resist using all the technical things. And so the most complicated thing we use is 0 times something equals 0. So that's why I like all that stuff.
Any other question, comments? Okay, so let's thank the speaker again. Thank you very much.